So I'm going to talk much more on an empirical level, less modeling, I think, and trying to really track the role of bioenergy in the whole forest and forest products market globally, because even though wood historically has been a major use of energy in the world, the energy world and the forest world usually they have different meetings, basically. But here's a place where they really do interact. This is a power plant in Northern California where they basically just burn anything that can burn to create energy. And so you see wood pallets that might have come from China, might have come from Montana. You see chunks of wood that had been left in the forest because they weren't useful for lumber, but they went back again 20 years later and dragged them out. You see all the sawdust from the lumber mill, but all that stuff is used to generate electricity that goes into the California grid. So right now there is no carbon capture, but at some point, energy, wood residues are of all types, from the forest, from the sawmill, from post-consumer use can be used for energy. So yeah, I just point out that wood is the #1 biomass that's used for energy worldwide. Miscanthus and sugarcane, I think, are actually a lot smaller because a lot of people cook with wood. But even at an industrial scale, it still is the #1 piece. And we've seen much more use of wood, especially in Europe, co-firing their coal-fired power plants. They are at a small percentage, and they can go anywhere from 10% fairly easy to actually pushing it much higher. So it can be part of that highly efficient, the boiler technology. But I think it's really important that, from my side, looking at this from more an economist point of view, is that growing wood purely for energy is never the ultimate value. No landowner is going to just sell his wood for energy because it's the lowest value crop out there. It's the lowest value product. So everyone says, I want really cheap feedstocks. Well, you grow trees for me. Trees grow energy really well, and they can stand up in hurricanes and things like that. But someone else was going to outbid the energy buyer, and I think that's the key issue here. And because it has many other uses. And some of them actually have more climate benefits than actually trying to use them for energy. Oh, that didn't come out that well. But anyway, I want to just think of a tree. I'm going to use kind of high school geometry rather than Nobel Prize winning physics or chemistry to think about what a tree looks like. So this is a picture of a tree, not nearly as nice as the one that's on the Stanford logo, my alma mater, but it helps to explain this. In a tree, there's really kind of 3 pieces of it foresters think about. The top one is really why forestry has been in the business. It's basically it's the middle piece where we're going to make 2x4s and lumber out of the middle. So it's going to be a big rectangular piece that goes up inside of a round log. Around that, which is kind of the yellowest picture, are what are called the clean chips. Those are when you take a round log and you cut it into rectangular pieces, there's going to be all these little pieces there. Well, that's what we actually make paper with in the United States, essentially. Or it can be used for energy. In California, we have no paper mills, and so all those chips, either if they can bid high enough, they go to paper mills in Oregon, or we burn them for energy for electricity. And then finally, there's what's at the top here is the top of the tree and the branches that are in kind of the big piece out there. And those are what are considered the dirty chips or the logging residues. So there's really 3 pieces, but it's really important. Historically, foresters, when we measured forest volume out there, we looked at a forest of trees and all we saw was the lumber. And we told people that stand has 20,000 board feet per the acre after we processed it. And so I went back and did some math with actual work in California, and about half the biomass in forests in California doesn't go into lumber. It goes into something else. And tracking that piece, historically, we just burned that in the forest. It wasn't worth moving, just emitted the CO2 instantaneously, or we just left it so that it rotted slowly. But so I think there's really 3 different pieces here, but each one of them has a very different climate benefit. And then when you really track from a life cycle, if you look at where does that lumber go, lumber's got big advantages. It's an insulating material. It grows itself, unlike cement and steel. And when it's put into buildings and they're built efficiently and tight, you can have very large energy carbon savings by doing that. The Europeans have done a lot of work on this, and across many different building products, they found for pretty much every ton of carbon that's wrapped up in the wood products, especially engineered products, they basically over the life cycle, they save a ton of CO2 compared if they'd use a cement and steel building. So there's a real huge savings, and I think that's really going to be the biggest energy climate benefit. The second is using some of those clean chips. This is what all the engineers want when they build these biomass energy facilities. they think they're going to use forest residues. That's what they tell, I think, their people, their investors. But their engineers say, I want a really clean fuel. And it's like, oh, the pulp industry has these standardized products of what are called clean chips. It's no bark, no weird chemicals, not many rocks. And that's what they designed those plants for. And it works really well. But it's a little bit more expensive. And finally, there's all this stuff we call dirty chips or logging residues that has the bark, it has the needles, it has the branches. So it's got this fairly strange chemical composition out there, and it really scares a lot of the chemical engineers. But it's usually cheaper. And this is the real key. From an economic point of view, what do we call these dirty chips? If they're a one, if they're $10 a ton, those clean chips, the market is about 20. It's about double. And then the value for lumber is double that. So it's a 1-to-4 ratio of the value of that tree. And I think that's really important when people think about wood for energy. No one's going to chip a whole redwood tree and turn it into lumber because they're an idiot. Well, actually, not many people are actually idiots. They sell the best part of the tree for lumber, the second best part to someone else who wants the clean chips, and the last goes to something else. And I think that's really important to understand that energy plays along with these other markets that are out there. This is a picture just where wood comes from in the world, and it did the green graphs. The green lines are what's called industrial roundwood, or wood that's actually goes through some processing for lumber or paper. The gray bars are really wood people are using to kind of cook and heat. And so you see that the biggest countries that actually produce products are not where we think of deforestation, which is Africa, Latin America, and Southeast Asia, but really are North America and Europe. I think that's really important to think that that's really where we do have a kind of forestry. And the question is that sustainable? And actually for the United States and Europe, it is. We're both, United States and Europe, very similar. We're growing about 1.6 tons of wood for every ton of wood we harvest on an annual basis. So the forests are getting thicker and thicker over time. Canada pretty much is even. They're pretty much harvesting as much as they grow. And Russia, you just pick a random number and you can find that statistic. No one knows actually what's going on with the Russians. But they got a lot of forests out there. But so there really is difference in how we think about how wood enters the system and how efficiently it's used. And in terms of long haul, can we repurpose some of this very inefficiently used wood to do something better? When I worked for 5 years in Asia, people cook with wood, but boy, as soon as they got paid a cash wage, they immediately shifted over to cooking with liquid gas because it was actually cheaper. And the only difference was the deposit on the cylinder is why poor people or they had free labor in their house to cook with wood. All of them shifted. As soon as they had the money, they shifted to natural gas. This is another graph. Now, this is just looking at some of the data. We've looked empirically, where's the annual production of wood in the United States, so where does it go? And I kind of stack them up by region. The South is where we produce most of our wood. Actually, the North is actually the second largest producer of wood. They don't harvest that much, but they're growing a lot. But that's where a lot of the pulp mills are. But when you look at it, if you stack it in terms of value, there's some of it, the blue at the top, those are the high-value saw logs. And then the ones that go for basically pulp. And then the green is the stuff that goes right now for fuel wood. And historically, is in 2007 data, there's just a lot of logging residues and mortality that's left out in the forest, which is a fairly large, it's about a third of that column. Of the annual net change in the forest, about a third of it is basically dead wood out there that we just leave to rot. In some areas, if you have deep soils and they're fairly fertile, you can take out a fair chunk of that because annually, when trees grow over a 60-year cycle, every year they're dropping leaves and branches out there to basically, most forest soils, you have to check with the forest soils, are actually sustaining at a pretty good level. California has very, very fertile soils in this regard. But this is just look at example of, I come from the United States and North America, look at it, but really in terms of productivity, probably Brazil is some of their eucalyptus plantations, some of the most productive systems in the world. Highly productive, the graph on the left, as you go a little bit, as it gets warmer, as your latitude numbers drop, the productivity starts to increase, but they just have phenomenal rates of productivity. Most of this short rotation eucalyptus is going directly into paper because the people that the biggest value in this game is the paper mill, is not the productivity of the product. They don't grow long enough to make plywood or oriented strand board. You could, if someone else owned the mill, but since the paper mill basically has the contract, they're still doing a fairly inefficient system, but it penciled out. They're making a lot of money. But this is extremely efficient. Brazil has some of the highest productivity forest lands, not in the Amazon. This is out kind of in what are now historically, or in the last 10 years ago, we're basically having cows run around and try to put some weight on. But one issue we've had a lot of this is collecting some of this biomass from the forest. Is it carbon neutral, or are we taking away live trees that would have been grown and we're turning them into fuel and something else? And I think that neglects the fact that we're already in the energy business. About 40% of the products that come out of the forest in the United States go to energy, not products already. We already know this. We already have the data. It's not some newfangled dangerous idea that's going to destroy the world. It already is out there. And there is a lot of good data. In a lot of cases, the wood that's left in the forest, if you have too many trees, they sometimes burn down in the west, like my friend's house who just burned down in Fort Collins. Or when they do harvesting, the Forest Service, they just leave these big, strange piles the size of a small house of debris that they just left in the forest, and it'll slowly rot unless it catches on fire. So these are just some of the challenges I'm dealing with that. We don't need to go through some of these issues. But this is an example, just empirically. I went back and looked at some landowners in California and kind of tried to track what happened when they harvested their forests and they replanted their, by law, they're on a sustainable level of doing that. And just the difference that we talked about, kind of the accounting rules. On the left here is basically when people say, well, they just use some of the old standard numbers, the generic numbers out of the, some used Forest Service reports assume that basically that no wood was used for energy, or very little of it. There are just huge piles of sawdust in the back of sawmills, which might have been true in the 1940s, but it isn't really true now. And I went back and looked at these sawmills and what they actually did. So what we did is I took 100 tons equivalent of wood coming out of the forest and tried to track where did it go. And over 100 years, only about 25% of it stayed in the products, or those products when they're in the landfill. A lot of products go out of use, pallets, the paper, people knock down their house and build a new deck, things like that. But if you capture, many places actually in California you do, a lot of that post-consumer residues is captured for energy. And also in the sawmill, there's a huge amount of all the waste when you take basically a cylindrical log and turn it into kind of rectangular pieces. A lot of that stuff that can't be sold for paper is used for energy. Most of it in California is used for energy. And here in California, where I looked at these studies, these are areas where California in the 1980s, we basically shifted to natural gas, and we gave a lot of bonuses for renewable energy. And so there was actually a market for taking this logging residue that essentially is worthless and basically covering the transport cost. But when you look at how much energy was produced by that energy, it's a pretty big chunk of that column. So when you kind of add up the energy and then give the bonus for actually building houses with wood rather than cement and steel, I'd say it's actually a kind of a negative carbon system. But it's only when you actually think about the energy as part of that system and you actually do collect it. In some places in the United States, it isn't collected. It's just all of us left out there. In places where there aren't strict landfill rules, they just have basically free-range landfills in Wyoming where it just slowly rots out there. But I think, so I guess my point is, that using that wood, replacing it cement in buildings is really probably the most valued use of wood products. But one problem is, we build houses with wood here in our subdivision in California, but most of the buildings built in the world in the next 10 years are going to be in Asia. And they're going to be, right now, they're building multifamily buildings out of reinforced concrete. And you really need a technology that's going to replace that. And actually, the Europeans have done a lot of work with what's called cross-laminated timber, which is like super dense plywood, to really get a product that you could actually build these buildings with wood, rather than having to use cement and steel. But I think there's a case where you can actually have the potential to use that wood to actually build the buildings where people are going to be living in New Delhi and Shanghai. And that really is the biggest challenge out there, I think. California, we still just think of building new subdivisions, but that really, most of the world is not going to live in Mountain View. And this is just kind of a graph of looking of the different products that are out there, where wood actually goes, to kind of give some sense. These are all traded, and these are priced from the South, which is probably the most efficient market we have for wood in the United States. And really the three big ones are, if you look at the value of the saw timber, the stuff that goes into the 2x4s, the 4x6s, and the wood we have. And then with the pulp is down here. And then they do have a fairly significant market for biomass. People are actually selling, these are delivered prices. These are delivered to some consumer's value. And the key thing in this one is, you just think, if you look at the prices, they go from, they're kind of that same rule of two, 100 to 50 to 25, or 80 to 40 to 20. They're really they jump down in kind of halves. And there's real different prices out there because there's competing uses for these products, and people have numbers. And people, hardwoods are a little bit less valuable, but here you see the hardwood timber, it's flatter because that goes into furniture, which is, people always buy in furniture. Pine saw timber goes into residential construction, so when it collapsed, that market dropped. So each market has its own, each non-energy market has its own special dynamics. We do actually track all this type of stuff, so it's not that, but it does make, engineers like do life cycle analysis with one number for the next 80 years, a million years, and it really changes on a kind of a quarter by quarter basis. So what I've been doing, we're also doing some work with the Energy Biosciences Institute up with Berkeley and Illinois. And what we're trying to do is try to understand how these markets work. We're not saying that wood should be used for energy, but if it's going to be a player in the market, it's going to be a player in the global market. And so how is that going to be produced? Because much of the surplus productivity capacity of wood is in North America. And where is that going to go? We have this huge issue. China has tripled its paper production in a decade. They don't have any trees that they want to cut down unless they want to see how much silt they can get in the rivers. So they're looking outside. For a while, they bought it all from Russia. Russia changed its export rules to try to make the Chinese build mills inside of Russia. The Chinese seem to have nerves of steel on negotiating contracts everywhere else in the world, but they decided not to deal with the Russians, and they basically started buying from Canada and the United States. They bought on the open market, basically stuff coming across by boat. So there's going to be a huge market playing out in this. So what we're trying to do is understand how these markets are going to work, and not just assume it's all going to go to product A or product B, but as economies grow, they're going to demand more wood, more paper, and more energy. And so this is just an example. We know, when we're trying to look really at the end, it's like how much wood's going to be available for fuel feedstocks. Right now, when prices are high, they're going to start, bidding at these higher values. But if it's just collection costs, people are going to start collecting fiber residues from the mills. In the United States, a fairly low cost, $32 a bone dry ton. Logging residues, you got to truck it farther to get that. And then finally, if other people are using it for fuel wood, if they can have some other way to cook their food, all that stuff's going to go into their feedstock. So we took a model that historically just considered fuel the last thing. The original model was built to track timber trade. But we said, wait, it's just fuel is part of that same international market, especially with Asia really demanding more products, more paper, and more energy. And so what we've been trying to do is break that huge generic fuel sector into the feedstock that can go into biofuels, the stuff that's going to go into the electric grid, and what's going to go into basically industrial heat. And I think the electricity, those are the ones I think that where there is some potential overlap with the carbon capture and storage. Cellulosic biofuel, I see that is really, you can't escape the fact that somehow we're going to need to power jets and big trucks. And I don't think we're going to have mega Priuses flying around anytime soon. So in conclusion, I want to say that I see energy technology as really, it's going to be the poor cousin of the building part of it. But that still means the other half of the tree is going to be available to be moved around efficiently. And we don't really know how this is all going to work, how it's going to be split between the three uses. But I do think there's going to be there's lots of good economic data to track this. But I do think this is going to be a piece of the puzzle, but that it's, we're trying to figure out how big a piece of that puzzle is going to be. So with that, I just want to thank you and open for question and answer.
You talked about the different uses for forest products and their different sort of values in carbon mitigation. Would it make more sense to try and, I guess, push out the boundaries on what can be put into engineered wood products into more of this sort of third grade, very low grade material, or use that in for electricity displacement, displacing coal?
Yeah, I would think when you actually do the math on this, the best thing to do with those clean chips that you can't put into dimensional lumber is engineered wood products. They usually have the highest replacement benefits compared to cement and steel because they're so strong in concrete. And they're using those products that you would have gone to paper just to burn it. So pretty much when people have done the math, that engineered wood products really, they're even better than the normal lumber because they're much stronger. They can actually replace cement and steel. Yeah, I think that probably is the really source with probably the largest upswing. And you know, and they will, if they can get that price, then they're probably going to be able to outbid the energy purchasers. For the
Is there a way to move the dirty chips into that kind of market, or is it too dirty?
Yeah, I'm not an engineer. Those guys, they're going to have to clean it and do it. They probably can. You know, it's an engineering problem. You just got to figure out how to clean the stuff. Some of it, it's not all dirty. You know, it's dirty because there's just 10% stuff in it. But if you figure out a way to get rid of the bark and some of the other stuff or things like that, it's still sold. It's just a little bit. You need a little bit more post processing.
Thank you very much for an interesting talk. I guess I was really surprised to see that North America and Europe as being, such major producers of wood and forestry and so forth. So what are the prospects of increasing wood production in other parts of the world and doing that in such a way that it doesn't negatively interfere with food or ecosystems or whatever?
Yeah, there are, South America, a slightly warmer climate, there's been the most productive new plantation forestry has probably gone into South America. There's been very little change in Africa. And places where you have lots of people that they want to put their labor to growing food or other things, that's probably now we're going to you put lots of trees where there aren't a lot of people. And so that's why there's, comparatively, there aren't that many people in North America and Europe compared to these other places. So that's, I think, why we are producing a lot. If you've spent much time in Asia, there's reasons why half the forests of India are gone. It's because they're growing rice now, and corn and wheat and beans and stuff like that. Because there's 1.3 billion people or wherever it is. But we don't have that problem, especially Canada. I mean, they're just endless source of
With climate change and with the increase in temperature, how is this going to affect the growth of some of these stands of trees and the carbon dynamics of these forests? I know that you have the beetle epidemic, you have various epidemics all over the place that are decimating these forests and really altering these carbon dynamics. So how does this play into the whole equation, and could you comment on that at all? Yeah,
well, in the big system, climate change, especially when you talk to the Canadians, they're and the southern Canadians are really happy because their trees are going to grow faster because it's going to be slightly warmer. The biggest changes is climate change will change the potential for really large wildfires in areas that are going to wipe out forests you've been growing for 60, 80, 100 years. And there are issues where, in terms of some of the issues of beetles and other things, where the natural forests, reason why the beetles they attack so well is because there was just basically too many trees for how much water was available. So if you actually thin some of those forests, you could increase the resiliency to some of those risks, but not all of those. So it's going to be very tricky, and every area is going to be slightly different on how to deal with those different risks and potentials. But a lot of it comes down to is water still going to be there? Because it's going to be warmer, but it might not. If you don't have more water, it doesn't really matter. And are the bugs going to grow faster than the trees? And that happens in a lot of places in the world.
Okay, I think we probably ought to go on.
Good.
Thanks very much.
Okay, thanks.